Hello, welcome. In the previous lecture, we discussed row space and column space of a matrix and rank of a matrix. In this lecture, we're going to talk about coordinates of vectors in a vector space and how do the coordinates of vectors change under the change of basis. Let's begin our discussion with the notion of coordinates. Let V be a real vector space. In theorem 11.1.1, we saw that if B is a basis for a vector space V, then every vector V in the vector space V can be expressed in one and only one way as a linear combination of vectors in B. The coefficients in the linear combination are the coordinates of the vector V relative to the basis B. We'll have a formal definition of coordinates shortly. In the context of coordinates, the order of the vectors in the basis is important. So, this will sometimes be emphasized by referring to the basis as an ordered basis. For example, if B is a set of these three vectors and B prime is a set of these three vectors, they are in fact same sets, and each set is a basis for the vector space R3. However, we will consider B and B prime are different ordered bases. Definition. Suppose B is a set of vectors is an ordered basis for real vector space V. If V is a vector in the vector space V such that it has the following presentation, then the scalars C sub 1, C sub 2 all the way up to C sub n are called the coordinates of the vector V relative to the basis B. Since the vector V has been expressed as a linear combination of the vectors in the basis B. The coordinate matrix or coordinate vector of the vector V relative to the basis B is the column matrix in the vector space Rn, whose components are the coordinates of V. We denote the coordinate matrix of the vector V relative to the basis B by this symbol, which is in fact the collection of the coefficients in this equation written in a column form. C sub 1, C sub 2 all the way up to C sub n from this equation. So this column matrix is called the coordinate matrix of the vector V relative to the basis B. For the vector x with components x sub 1, x sub 2 all the way up to x sub n in the vector space Rn, the x sub i's are called the coordinates of the vector x relative to the standard basis S with the vectors e sub 1, e sub 2 all the way up to e sub n. Recall that e sub 1 is a vector with components 1, 0, 0 all the way up to 0. So it has n many components whose first component is 1 and the rest of the components are zeros. Similarly, the vector e sub 2 has the second component 1 and the rest of the components are zeros, and so on. So we can express the vector x as a linear combination of the vectors in the standard basis S, as shown in this equation. So the coefficients x sub 1, x sub 2, all the way up to x sub n, written in a column form, gives the coordinate matrix of the vector x. In this case, the vector x and the coordinate matrix corresponding to the vector with respect to the standard basis are exactly the same. This would not always be the case. We will see some examples shortly. In this example, we want to find the coordinate matrices of the vector v with components -1, 2, 3 from the space R3 relative to the following ordered bases for R3. The first basis, as we recognize as the standard basis for this space R3, and the second basis B is a non-standard basis for this space R3. Let's have a look at the solution. As we mentioned just a moment ago, the coordinate matrix of the vector v relative to the standard basis S is exactly the same as the vector itself. Since B is the basis, there exist unique scalars C sub 1, C sub 2, and C sub 3 such that the equation is true. Now, if we replace V sub 1 by the vector with components 1, 2, 3, and V sub 2 by the vector with components 0, 1, 2, and similarly V sub 3 and V by the vectors with components -2, 0, 1, and -1, 2, 3 respectively, we get the following vector equation. To solve this vector equation for the constants C sub 1, C sub 2, and C sub 3, we'll form an augmented matrix for this system. Let's try to write the matrix form of these equations. The left-hand side of this equation can be put into this form: the product of a 3 by 3 and a column matrix. And the right-hand side stays the same. The augmented matrix corresponding to the matrix equation 1 takes the following form. And if we apply a sequence of elementary row operations as shown, we can reduce it to this reduced row echelon form. Here we identify the pivots. This shows the values of C sub 1 equals to 3, C sub 2 equals to -4, and C sub 3 equals to 2. Therefore, the coordinate matrix of the vector v relative to the standard basis B is given by equation 2. This example shows that the procedure for finding the coordinate matrix relative to the standard basis is straightforward. But it is more difficult to find the coordinate matrix relative to a non-standard basis B, since it was involved with the applications of sequence of elementary row operations to reduce the coefficient matrix to its reduced row echelon form. Let's have a look at another example. In this example, we want to find the coordinate matrices of the matrix A taken from the vector space M sub 2, 2 relative to the following ordered basis for the vector space M sub 2, 2. As before, here the set S is the standard basis for the vector space M sub 2, 2, and the set B is a non-standard basis for the vector space M sub 2, 2. Since the matrix A can be expressed in terms of the matrices in the set S as shown, therefore the coordinate matrix of the matrix A relative to the standard basis is the collection of the coefficients written in order but in a column form. So the matrix A with entries -2, 7, 3, -4 has the coordinate matrix relative to the standard basis S -2, 7, 3, -4. This is an element in the space R4. Now, to find the coordinate matrix of A relative to the non-standard basis B, we need to solve the following matrix equation for the unknowns C sub 1, C sub 2, C sub 3, and C sub 4. The left-hand side of this matrix equation can be put into a single matrix, and the right-hand side remains the same. Since these two matrices are equal, we must have C sub 1 plus C sub 2 plus C sub 3 plus C sub 4 is equal to -2. So we have an equation which, when reduced to its reduced row echelon form by applying a sequence of elementary row operations, has this form. This gives the value of C sub 1 is 2, the value of C sub 2 equals negative 9. Similarly, the values of C sub 3 and C sub 4 are negative 5 and 10 respectively. So if we write these coefficients into a column matrix, it gives us the coordinate matrix of the matrix A relative to the basis B. So we see that the matrix A has this coordinate matrix relative to the basis B. Similarly, we can find the coordinate matrices of the polynomial p of x equals negative 6x squared plus x minus 3 from the vector space p sub 2 relative to the following ordered bases for p sub 2. I highly recommend you to try this problem. With this, we end the part 1 of this lecture. In the upcoming part, we're going to talk about the change of basis and how do the coordinates of vectors change under the change of basis. Thank you.